All right, now we get into the meat of this graph theory. Now that we've done a bunch of defining things, now we actually put it to use to solve problems. And one of the problems is to find what's called a minimum spanning tree. So let's talk about what that means to find a minimum spanning tree. A tree is basically what you think it is. It's a subgraph of the original graph that has no circuits and no cycles in it. So there's no looping, there's no, basically what it says, circuits or cycles. A spanning tree is a certain tree, which we've already defined, that has all of the vertices of the original graph. So you have to include every single vertex that was already there. You don't have to include all of the edges, obviously, but all the vertices have to be there. So what we do now is we assign each of these edges a weight, and maybe the weight is either the length of that road, or it's the cost of traveling that road, or something. There is a certain weight or cost assigned to it. And so what we want to do is we want to be able to get from every vertex to every other vertex using a tree, but we want to use the one that has the lowest possible weight. Okay? So there are a couple of people that came up with different algorithms to do this, but I'm just going to give you an example of here's a weighted graph. It's got 7 vertices, and each one of the edges has a cost associated with it, and that cost can mean a different thing depending on the problem. And what I've done is I've listed the adjacency matrix beside it. So any 2 vertices that are not connected to each other using one edge have an X, and then every 2 vertices that are connected with an edge have that number as its element. So you can see this 7 represents the edge from A to C, for example, and there's the edge from A to C, and it has a weight of 7. So setting up the matrix is, it helps. Just know that there's some symmetry to it. All right, the first guy that came up with an algorithm for finding the minimum spanning tree was Kruskal, and so his is associated with edges. Kind of like Euler was focused on edges, Kruskal is also focused on the edges. So we're going to pick our minimum spanning tree by just looking at the edges. So what we do is we start with the shortest edge, and if there's a choice, you just make a choice. There may not be a unique minimum spanning tree for any problem, so you just find one of the minimum spanning trees. And there may be more than one way to do that. And we keep choosing the shortest remaining edge that's left from the ones I haven't chosen yet, as long as it doesn't make a circuit with the edges that I've already chosen. All right, and I just keep doing that until I've got n minus 1 edges, n meaning the number of vertices. So I'm going to keep going. In this case, I've got 7 vertices, and I'm going to keep going until I have 6 edges, and then I'll be done. All right, so here is an edge of weight 1. That's the lowest one that I have to choose from. And I've got 1 edge. I've got 2 edges that are of weight 2, and neither one of them are going to form a cycle with what I already have. So I can choose both of those. Now I have 3 edges, and I've got 3 to go. The next one is 3. All right, so I can use that edge. It didn't create a cycle. Now I've got several choices. I've got 3 edges that have weight 4. Well, I'm not going to pick this top edge that has weight 4 because that's going to make a cycle right here. So I'm going to either pick this 4 or this 4, and it really doesn't matter. So I'll pick this bottom 4. But what that means is I now can't pick this other 4 because now I'm going to create a cycle. So I'm done with the edges of weight 4. All right, so this was a case where I didn't have a unique minimum spanning tree, but all minimum spanning trees will have the same weight. So I'm done with the 4s. I move on to 5. Okay, and I use that one. And if I count my edges, I've got 6 edges. So now I'm done. And as you can see, every vertex has been connected to the graph using one edge or another. This graph is connected. I can get from one vertex to another. It is the lowest weight. I just need to add up all the edges to see what the weight of that subgraph is. So I've created a really good minimum spanning tree. That is Kruskal's algorithm. Now I'm going to use Prim's algorithm, and he focuses on the vertices. So what we do is we just start with any vertex as the start of our graph. So I'm going to start with this, I don't know, this one right here. Okay, so that's the vertex I'm going to start with. And I'm going to let this T be a set of vertices that I've already chosen. So I've only chosen one. And so what I'm going to do is I'm going to look at the edges where one endpoint is one of the vertices I've already chosen, and the other one is not a vertex that I've already chosen. And I'm going to pick the smallest weight out of all of those. Well, this is my only vertex, so the edges I have to choose from are the ones that leave this vertex. So I've got the 7, I've got 4, 2, and 4. Well, of those, the smallest is the 2, so I'm going to use that edge. So now what I've done by drawing that edge is now I have 2 vertices in my set T that has all of the vertices I've chosen. So I'm going to look at all of the edges that either leave the one at the top of this red edge or the one at the bottom of this red edge. So looking at all my choices, I've got 7, 4, 4 from the top edge, and I've got 4, 3, and 9 from the bottom edge. Well, of those, the smallest was 3. All right, so now I have 3 vertices in my set T, and I'm going to look at any edge that leaves one of those vertices and goes to a vertex that I haven't chosen yet. So I'm not going to use this 4 because it leaves this red vertex and it joins up with another red vertex, so I don't want that one. So I'm going to look at 7, I'm going to look at 4, I'm going to look at this 4, I'm going to look at 9, and I'm going to look at 1. Well, the smallest of those is the 1, so I will choose 1. Okay? And my choices are getting smaller. So let's look at what I have left. I can't really choose anything that leaves this vertex. I can't really choose anything that leaves this vertex because it's going to join with another vertex that I've already chosen. So let's look at this vertex. This has an edge of 7 attached to it and an edge of 4, and this one has an edge of 4. So I can pick either one of those edges of length 4, and I'll just randomly choose that one. So now I've got a choice of 7 or 2, and I'm going to choose 2 because that's the smallest. And now I have a choice of 5 or 7, and I'm going to use 5 because that's the smallest. All right, and there's my minimum spanning tree. It's very similar to the one I created using Kruskal's algorithm. The only difference is I use this edge of 4 instead of this bottom edge of 4, but obviously if I trade in one edge of weight 4 with another edge of weight 4, the weight of the graph is still the same. So I created a minimum spanning tree of equal weight to the one that I created using Prim's algorithm. So they both create similar trees with exactly the same weight. All right, now here is a much tougher problem. This is not about creating a minimum spanning tree. This is about finding the shortest path from one vertex to another. All right, so let's say I wanted to get from predictably A to G. Okay, so here is vertex A and here's vertex G. I don't need to go through all of the vertices to do that. I just need to find the shortest path that gets me from vertex A to vertex G. So here's what I do. I use my pen and I assign a weight of 0 to my starting vertex because that's the shortest path that it would take to get from A to A. I wouldn't have to go anywhere. So that's a weight of 0. And I'm going to draw a box around it, meaning that I have found the shortest path from A to A, and it is just to stand still. Don't know where my dot went at this point, but that's okay. What I'm going to do is I'm going to look at all of the unboxed vertices that are connected to the vertex that I just boxed. Okay, and I'm going to label them with the minimum weight from the starting vertex. And I'm going to, for the first time it's going to be pretty easy, but then after that I've really got to pay attention because it's kind of complicated. So this edge B is connected with a weight of 5, and this vertex B is connected with a weight of 5, and C is connected using an edge of weight 7. All right, and so I'm going to choose the least of these, and I'm going to put a box around it, and that makes it permanent. All right. So now what I do is I go back to step 2 and I look at all the unboxed vertices that are connected to B. All right, well, there's only one, and that's D. And so the shortest way to get from A, I'm always starting with my A. The shortest way to get there is going 2 more, making that a 7. Okay, so that's really the only way to get there. All right, now things get tricky. So now I'm going to look at all of the unboxed vertices. So now I've got a choice of C or E. Okay, so I've already labeled C with 7, but actually there's another way to get there, and that would take 5 plus 2 plus 4, which is 11. That doesn't beat 7. 7 is still shorter. So I'm still going to have a label of 7 at vertex C. Now I look at getting from D to E, and that's 4. It already took me 7 to get to D, so to get to E, that's 11. So I have a choice of getting to vertex C with a weight of 7 or getting to vertex E with a weight of 11. Well, obviously I'm going to choose 7. All right. All right, so now starting at C, I'm going to look at all of my vertices that I haven't chosen yet. So getting from C to E would be 7 plus this 2. So that's actually now a weight of 9. And then getting from C to F, that would be a weight of the 7 that took me to get to C plus 4 more. So that's 11. All right, and there are no other vertices that attach to C that I haven't already boxed yet. So E with a weight of 9 is the shortest way so far. Okay, and now from E, I can either go to F or I can go to G. Well, if I go from E to G, that's 9 more, making that 18. And then I can also go from E to F, which would be the 9 that got me to E, and then 3 more, making that 12 to get to F. But I've got a better way to get to F, right? I could go 12, but I've already figured out a way to get to F that only costs me 11. So I'm going to use the path to F that only costs 11. And so now F was my last choice. The only other thing I can do is take this path of weight 1 to get to G, and that will cost me 12. All right. So I need to remember what my path was here. So I started at A, and I think I went to C from there, and then to F, and then to G. And that whole path cost me 12, which was the lowest or cheapest way to get from A to G. And that is Dijkstra's algorithm. By far the most complicated of the 3 algorithms, but once you do plenty of examples, it gets easier. So if you have any questions, let me know, and I will see you tomorrow.